Okay, today we're going to talk about inverse trigonometric functions. We want you to learn how to evaluate and graph the inverse sine function and all the other 5 inverse trigonometric functions. And then we want you to also be able to evaluate and graph the compositions of inverse trigonometric functions. That should say inverse. Okay, first let's start off with the inverse sine function. And if you remember from your time in geometry, hopefully you covered inverse functions, and those were what we used to find measures of angles. So instead of finding lengths of sides with our regular trigonometric functions, we could find the measures of angles with inverses. Now, we didn't really go too much into it back in geometry because it was a rather complex subject. But now we are going to do that. Now, if you remember, the definition of an inverse is where we actually trade the domain and ranges between our two functions. Well, as we can see here, sine is a periodic function. It keeps repeating. So if I were to reflect that over the line y equals x and trade its domain for its range, I would get a function that kind of goes like this. Well, as you can see, this would not be a function. It would not pass that vertical line test. And so we can't just simply reflect that whole sine function across the line y equals x. So we say, well, how much of this sine function can I reflect across the line y equals x and still have something that meets the definition of a function? So we find that we can do this with just a small section of sine, and that's this section right here, okay? And that corresponds to this section right here. And so my starting point for this is negative pi over 2, and my ending point here is positive pi over 2. Okay? And that section is a section that we can flip over that y-axis, or that line y equals x, trade the domains and the ranges, and actually get something that is a function. And so we get this inverse function here. Okay? So instead of sine of an angle equaling a ratio, we have inverse sine of a ratio equaling an angle. And that's what we call arc sine or inverse sine. Okay? So y in this case is an angle, and x is a ratio. Okay? And this only applies if sine y equals x. Okay? So another good way to write this would be an angle equals arc sine of a ratio, okay, if and only if sine of that angle equals the ratio. Okay, so we're actually physically changing these domains and ranges around, okay? Now we are going to get values, our inputs can be anywhere from -1 to +1, okay, because ratios will always take that form. And my angles will result in something between negative pi over 2 and positive pi over 2. And putting that in degrees, it's -90 to +90. So that will be my domain and range of my inverse sine function. And when I'm graphing inverse sine, sometimes it's helpful to actually graph my sine function and then flip that over the line y equals x to graph inverse sine. Okay? So when we graph inverse sine, our input normals our input values are the normal output values for a sine function. So we can't exceed 1 or negative 1, right? Because my normal sine function does not exceed 1 or negative 1. And my output values are going to be my angles. And we talked about this on the other slide. My function is limited because, of course, we need to pass the vertical line test once we have created our function. So one of the suggestions that I have for you is to work in exact calculations instead of approximations. And this is where the chart that we hung on the wall in the back of the classroom will really help, okay? Because we can take inverse sine of any number of things. Like say I wanted to take inverse sine of 1/2, okay? Well, I know from looking at the chart on the wall that that will equal pi over 6 radians, okay? Now, that's just working the chart backwards, okay? But I also know from my chart that that's just dealing with reference angles. Now, sine is going to be positive in the first quadrant and in the second quadrant, so I actually have another angle that would give me an arc sine of 1/2 equals pi over 6. And that angle is going to be 30 degrees in the second quadrant, which is 5 pi over 6. Okay? So we have to keep in mind that there is usually a second solution to my inverse sine problems. So now let's look at other inverse trig functions. This function is inverse cosine, and sometimes it's called arc cosine. Okay, so my angle is going to equal arc cosine of a ratio if and only if cosine of my angle equals that ratio. Okay, my domain is going to be -1 to 1 because the domain of cosine, or the range of cosine, is from -1 to 1. Okay, so remember arc cosine or inverse cosine and cosine flip, they exchange domain and ranges. Now my range is going to be a little bit different from here for this. So arc cosine actually has a range from 0 to pi. And you can see this here from 0 up to pi, 3.14. Okay? Now, my magic points that get translated over, or reflected over, are 0 to 1 and this section down here. So if we look at it, that is just this portion of my cosine graph. And that's the only portion that I can reflect over the line y equals x and still get a resulting function. So let's do another similar example problem with this. Let's try to find the arc cosine or the inverse cosine of 1/2 again. Well, we see with cosine that's going to happen at pi over 3 radians, and we know that cosine is going to be positive in the first and the fourth quadrants, and so we're also going to be dealing with let's see, 3 pi, 4 pi, 5 pi over 6. No. 5 pi over 3 radians. 5 pi over 3 radians. Okay, so that's 60 degrees in the first quadrant and 60 degrees in the fourth quadrant. Will both give you a inverse. Those will both give you a cosine of 1/2. Okay, so inverse cosine of 1/2 will equal one of those two angles, or both. Actually, both of those two angles. Now let's look at inverse tangent. Inverse tangent is a little bit different. Now tangent is also a repeating function, and we see that its period is every pi radians. Okay, but tangent, because it is does not have it's not one of the squiggly functions. That's a good way to say that. It's not one of the squiggly functions per se. it actually has a range from negative infinity to positive infinity. So that means my domain in inverse tangent will be the same, okay? Now my range is kind of limited from negative pi over 2 to positive pi over 2, but that's okay, okay? There's no real craziness going on. It's just that inverse tangent is going to be this purple line here, okay? So we have one instance of tangent. It does have domain of any real number, but the range that you're going to get out of it is going to be a little bit more limited. So let's take a look at an inverse tangent problem. Let's find the inverse tangent of, let's see, square root of 3. Okay, well, square root of 3 happens at pi over 3 radians, right? But we also know that it is going to be, tangent is going to be positive in the third quadrant. So with a reference angle of pi over 3 in the third quadrant, we are looking at 4 pi over 3 as well, being an answer for tangent, inverse tangent of square root of 3. Okay? So we have still more inverse trig functions. We do not actually cover them in the text, but they all exist, and I wanted to let you know what they were and what they looked like. So here we have secant in blue. We have our line y equals x, and here is arcsecant. Here we have, cosecant is in blue on this one. I said it backwards. Cosecant, right? And here we have arccosecant. And here we have secant and arcsecant. And then cotangent is in blue here, and arccotangent, okay? They're not covered in the text, and they're not testable, but they do exist, and you can see the functions on your calculator under the trig button. So I wanted to let you know what they looked like in case you were curious. Let's talk about the inverse properties of trig functions as well. Just like other inverse functions, if I take the sine of an arcsine of something, I'm going to get my original value. Likewise, if I take the arcsine of the sine of a value, I get my original value. Same goes for cosine and tangent, okay? Any two functions where I take the inverse of that function as the input for my function, they kind of negate each other out, okay? So it's like taking the square of a square root or the square root of a square. They negate each other out because they're inverse functions, okay? So we have the same properties going on between sine arcsine, cosine arccosine, and tangent and arctangent. Now, you might have some different types of problems that deal with these, okay? So say I want to take the arcsine of the sine of pi over 3. Well, that's just going to be pi over 3, okay? But we can also take the arcsine of the tangent of something, okay? So let's look at some of these composite functions. Okay, so let's take a look at the secant of the arcsine of 4/5. So if I draw out a triangle, a 3, 4, 5 triangle, we know that sine of theta is opposite 4 over hypotenuse 5, which means my adjacent side will be side length 3. Now, the arcsine of 4/5 is this theta, okay? So arcsine of 4/5 equals theta, and we can see that on our drawing. Now we want to take the secant of theta. Well, the secant of theta we know is just going to be hypotenuse over adjacent, okay? So the secant of the arcsine of 4/5 will actually be 5/3. You might have problems like this where you have to break down different values and combine different functions like this. So don't be afraid of that. We'll do some more of this in class. What we've learned to evaluate and graph the inverse sine function and also inverse cosine and inverse tangent functions. We've learned that inverse cosecant, secant, and cotangent also exist. And then we've done a little bit with compositions of trigonometric functions. This is not going to be a tough chapter per se, or lesson per se, but it will kind of twist your brain a little bit. So let's get some practice with doing these types of problems in the practice work, and make sure you ask lots of questions if you're having problems with this. That's it for now.